Hi, this is Prasanna from Wave Academia. In this video, we are going to discuss about how to simulate closed loop buck boost converter using Matlab. Straight away, I'm going to the Matlab. So in this closed loop buck converter simulation, the controller I'm going to use is a PI controller. Let us see how to do that. First, I will develop the buck boost converter, and then we'll move on to the closed loop. I need some components to develop the circuit. First, I will take that components. I need a series RLC branch. So from that, I need three components. One is for capacitor, and one is for inductor, and one is for the resistor. Values and all I will put it later. So this is nothing but my capacitor. This is inductor, and this one is load resistor. Fine. So first I will do this simulation with the constant input. Okay, constant input, and then later I will do it with variable input. Okay, so I'm just taking a DC voltage source. I need a switch IGBT with diode. So if you look at this IGBT, it's having four terminals. Actually, M is nothing. It's not a terminal. It's a measurement port. It's having a collector, emitter, gate terminal are there. I don't want this measurement port. Double click on IGBT. Disable this measurement port. Okay. So this is nothing but the switch, and I need a diode. So here also anode cathode terminals are there, and moreover M port will be there. The purpose of M port is if you want to measure the diode voltage, diode current, you can use this measurement port to see the outputs. As of now, I'm not using that port, so I'm disabling this one. Okay, fine. Now I'll connect the circuit as per the diagram, as per the buck boost converter circuit. I am flipping this diode. Sorry. Actually, this is the circuit of buck boost converter. Switch will be on input side, whereas diode will be on output side, but the diode will be in reverse mode. Inductor will place in between input and output side, and then you are having a capacitor. At last you are having the load resistor. Now I want to measure the input voltage and output voltage, so I'm using voltage measurement. Similarly, I want to measure the output voltage across the load. I can see the output with the help of scope. I'm double clicking it. I'm changing the input terminals, number of input terminals, because I want to see, I want to compare both input and output. I'm changing this as 2. The first terminal is connected with the input voltage, whereas the second terminal is connected with the output voltage. Here, one of the important thing you have to make a note that the output of buck boost converter, actually if you look at the relationship between the buck boost converter, it will be output in, I'm talking about input and output relationship, that will be output is nothing but V naught is equal to minus V in into D. Actually here this D is nothing but it's a duty value divided by 1 minus D. So this is the equation which represents the input output relationship of buck boost converter. Actually here the negative symbol comes into picture. If you want to make this negative symbol as a positive, then I have to use the absolute terminal, absolute element in Matlab. So what this absolute will do is absolute of 5, say absolute of 5 is nothing but it's a 5, and similarly absolute of minus 5 is also positive 5. So the absolute will treat all the values as a positive element. So I'm going to use this absolute to overcome that negative element in the relationship. I'm using absolute terminal, absolute element. So you have to use this absolute in buck boost converter. This is not mandatory in, not necessary in boost and buck converter. Now, since it is a closed loop, I'm having a set point. I can say that with the help of constant, I will declare my set point. So this is nothing but my set point. Or you can say it is a reference. Okay. So here I am fixing my set point voltage is 20 volts. I'm fixing that set point voltage is 20 volts. I said okay. Now I want to compare the set point with the measured value with the help of comparator. So for that I'm using some block. So in this one I'll change the terminal places for my convenient. So I'm applying it. So now this is the reference or set point. That set point is now compared with the measured value. This is the measured value. Now this one is comparator, or you can also call it as error detector. Okay, actually the output of comparator is nothing but it's a error signal. This error signal is given to the PID controller. So next block will be a PID controller. Okay, I'm just flipping this one. The output of comparator, that is nothing but the error signal, is given to the PD controller. But here the output of PD controller is control signal. You cannot directly connect this control signal with the gate source. The reason is the control signal, it won't be actually a gate signal. It's a switch actually. Whatever we are using IGBT is nothing but a switch. So I have to make the switch on and off with the help of pulses. How to do that is I have to generate the pulse. I am using a repeating sequence. Okay, so this repeating sequence is nothing but it's my carrier signal. Okay, I have to compare this carrier signal with the PD controller output, that is nothing but the control signal. I'm going to use a relational operator. So whenever my repeating sequence is lesser than the carrier signal, actually here the carrier signal is sawtooth generator. Okay, so this is sawtooth. Whenever the sawtooth signal is less than or equal to the PID control signal, at the time I'm instructing the circuit to generate the gate pulse. That's all. Okay, so now let us fix the values accordingly. I need a power guide. Okay, fine. Now I will put the values. So in this power guide, I'm going to use discrete power guide, and then I need 5 e power minus 7 is my sample time. And then go to modeling. I will do some changes in my configuration parameters, because then only the system will work fine. So solver selection, let it be variable step, and I'm going to change the solver type as ODE23T, and then I'm going to change the relative tolerance value is 1 e power minus 5, and then I'll change algorithm will be a adaptive algorithm, applying it. Okay, so now the configuration parameters has changed. Now I will let you know what are all the values. So this is a output voltage irrespective of input, whether the input is high or whether the input is low, that doesn't matter. This buck boost converter will give you the constant or a reference a reference or set point as a output. Suppose if the input is low, say if the input is 12 volts, for an example, if the input is 12 volts, then this buck boost converter will work in boost mode, which will give you 20 volt as output. Suppose if your input voltage is higher, say it is 30 volts, then this buck boost converter will work in buck mode, which will give you 20 volts as output. So based on the input, the circuit itself, it will decide, this controller will decide whether this buck boost will work, either it will in which mode it has to work, either in buck mode or boost mode will be decided by this PD controller. Now let us see. So as of now the power guide is over, the configurations are over. I am giving some input voltage, say it is 30 volts. Say it is 30 volts. Applying it. So my input voltage is higher actually. The set point or reference is 20. Then definitely we know that this circuit will work in buck mode. Let us see whether it is working or not. So inductor value I'm going to fix is 75 e power minus 6, that is 75 micro Henry is the inductor value, and the capacitor value is 250 e power minus 6. 250 microfarad is the capacitor value, and then the low resistor I'm going to use is 50 ohms. It's a 50 ohms, fine, right. So now the set point is 20, which is already given, and I'm going to change the repeating sequence parameters, that is nothing but my carrier signal parameters. The time values are 0 and 0.00004, which indirectly represents the frequency of my carrier signal. Okay, so this is nothing but a time value. If you want to know the frequency of the carrier signal, the formula is f is equal to 1 divided by t. Okay, if you want to find out, you can easily find out. The t is given here, so which will indirectly represents the frequency of the carrier signal, and the output values are 0 to 1, and this is nothing but the PD controller. In this PD controller, I'm going to use some KP, KA, KD values. I'm going to use the discrete PID, and then the proportional gain. What I'm going to use is 0.45, and the integral value is I'm going to use 43.5. Okay, so proportional gain is 0.45, integral gain is 43.5. Let it be derivative is 0. So that means I'm going to use only PI controller. Initialization, no need to change. Go to output saturation. We have to fix the upper limit and lower limit. Lower limit, let it be 0.1, and upper limit is 0.9. Apply it. Okay. Yes. Now, if you want to see the output in exact manner, I'm going to scope. I will change the style of the scope. I'm changing the figure color. This one is black. Axis color is also white, and pen color is black. Channel 1 is your input voltage. I want the thickness to be 2, and I will change my input voltage is black, and I'm applying that. I'm taking the channel 2. Channel 2 is the output voltage. I'm selecting the value. The thickness is 2, and I will fix some other color. Apply it. Okay, fine. If you want, you can add the legend. That we'll do later. Okay, now the input voltage is 30 voltage. The set point is 20 volts. Okay, let us see how actually the signal system is working. I'm changing this stop time as 5. Run the system, it will work fine. Of course, if you look at this, the black one is your input voltage, whereas blue one is the output voltage. So it is working in buck mode. And if you want to add, I'm just stopping the simulation. If you want to add legend, you can add it. Say this one is black one is input voltage, and then blue one is output voltage. Fine. So I just stopped the simulation because it will continue the same one. Okay. So now if you are giving the input voltage, the previous input voltage was 30 volts. Now if you are giving 15 volts for an example, because my set point is 20, so then definitely this circuit will work in boost mode. Let us see. If you run the system, of course it's working fine. The black one is input voltage, whereas the blue one is output voltage. So now this system is working fine in closed loop. Suppose if you are giving a variable input, the system is working fine. I'm stopping the system. I'm stopping the simulation. Okay. Now, instead of this constant DC voltage source, if you give variable input, for that also this closed loop system, the PID parameters will work properly. Let us see how to do that. So for creating a variable input, I'm going to use a component called signal builder. Okay, signal builder is a component which will be used to generate different kinds of signal with respect to time. Okay, if you look at this signal builder, if you double click this signal builder, you can able to see, go to signal, go to new. If you want to create a, if you want to develop constant, step, pulse, square, sawtooth, sampled, sinusoidal, or if you want to generate some noises like Gaussian noise, Poisson noise, something like that, you can do with the help of signal builder. But I'm not going to use this one. Instead of that, I'm going to use a custom. I will develop my own signal. Go to custom, set the time values and y values. Here I can say that 0, 1, 1. So here the time values totally are given 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here the time value should be matched with the length of time value should be matched with the length of y values. Otherwise it will throws you error. Let it be. So I'll give the values accordingly, that the circuit will both work it will work in both buck mode as well as boost mode. In such a way I'm giving the values. I'm starting with 0.6 and then 0.8. So how many values are given? 1, and then last values I'm giving is okay 0.75, 0.75. So these are all the values which are given: 0.6, 0.6, 0.8, 0.8, 1.6, 1.6, 1.8, 1.8, again 0.75, 0.75. Click OK. So this will be the signal. I'm just deleting the previous signal. This will be a default one. Okay, I'm deleting this one. I don't want this one. So this is the signal which I generated. I'm going to access, change the time range. Let it be maximum time is, let it be up to 6. I want only up to 6 seconds. So here, so if you look at this amplitude of this signal builder, it changes from 0.6 to 1.8. So what I'm going to do is, I'm going to multiply all these amplitude values with a gain element of, gain value of this set point, that is 20. So this will actually give you the input signal, input voltage. So I'm going to multiply the amplitude of this signal builder with the gain of 20. That 20 is nothing but my set point. That will give you the output voltage. Save this one. And I'm going to use a gain. So the value of gain is nothing but the your set point value, 20. And I need a controlled voltage source. So this controlled voltage source, which will help you to create, it will generate the voltage equal to the signal, equal to this signal. Okay, so this is nothing but it's a controlled voltage source. Just connect the output of signal builder to the S port. Now the plus is given to the positive and minus is given to the negative accordingly. Now the variable input is given. So accordingly I will do some manipulation here. I'm using some gain. I'm flipping it. The value of gain is nothing but it's 1 by 20. So whatever this, that 1 by your set point, 1 by reference. Okay, so this is for only for some manipulation. Fine. Now the closed loop buck boost converter is ready for with a variable input. Let me run the system. If you look at the output, this circuit will automatically work in buck mode as well as boost mode according to the input variation. Still the circuit is working in boost mode only because my input is lower than 20 volts still now. So it is working in boost mode. Now you look at this, my input voltage is changed from around 16 volts to 33 volts. So now at this point the converter is working in buck mode. So up to now this worked in boost mode. After that here it's working in buck mode. So irrespective of what we can keep know is irrespective of input voltage is higher, whether it is higher or lower, this buck boost converter will give you the constant output. The real-time application of this buck boost converter is you can use in, for an example, if you take electric vehicle, you can use this closed loop buck boost converter as a output circuit of battery, because in battery the battery will always give you the output voltage depends on the state of charge. If the state, for an example, if you consider a 48 volt 20 ampere hour battery, lithium ion battery, 48 volts battery, when the state of charge is at 100 percentage or nearly 90 percentage, then the output of battery it will be some around 56 volts. Whereas when the state of charge is at about to 10 percentage at the time, the battery output will be only 42 volts. So the output of battery is a variable one between 42 volts to maximum of 56 volts. But I need a 48 volts as an output, constant output. In such cases, you can use this buck boost converter in closed loop, which will help you to get the nominal output voltage of battery in electric vehicle. So this is one of the real-time application of buck boost converter. Fine. The system is working good. I'm stopping the simulation. I hope that this closed loop buck boost simulation will really help you to develop the model. Kindly subscribe the channel videos, and in upcoming videos we'll see with some different concepts. Thank you very much.